Hello everyone. Today I'll be presenting arming the next generation of spaceflight embedded platforms through processor reusability. This is a part of the class EE517 Digital and Computer Systems Architecture. And I would like to thank Professor Said for his support towards this course. This work evaluates whether a single ARM Cortex A72 processor architecture can be applied across a wide variety of spaceflight missions, improving consistency, reducing cost, and simplifying engineering efforts. So let's get started. Space missions are becoming increasingly complex and require significantly higher computing performance while still meeting strict power budgets and radiation tolerant requirements. Today, many different space rated processors exist, and mission designers often select a unique processor for each project. This approach leads to duplicated effort, which means new optimization, new drivers, and new software tuning every single time. So the big question becomes, can we standardize on one high performance flexible architecture? This is where ARM Cortex A72 comes in. The goal of this paper is to test whether this processor can satisfy the computing and power constraint of multiple mission types, enabling a reusable, unified platform. The ARM Cortex A72 offers a modern, efficient architecture that can scale across many embedded systems. Using a common architecture has several benefits. First is the software usability. Engineers can optimize OMS and reuse them across missions. Then comes reduced development time, which means less rewriting of drivers and mission software. Also, consistent memory and CPU behaviors, thus easier performance tuning and debugging. Lastly, reusable Linux customization. Instead of building a new Linux distribution for each processor, engineers can adopt one optimized version. This is especially useful because embedded systems involve tight software-hardware relationship. So if the hardware can be standardized, the software design effort drops dramatically. Power is one of the strictest constraint in spacecraft. The ARM Cortex A72 provides a rich set of features to dynamically control power usage. First, we can mention power gating, which involves turning off unused cores entirely. Then comes dynamic retention states. Here, the cores stay in a low power wait state, but respond to events quickly. And lastly, clock gating. This means reducing switching activity for lower dynamic power. Also, by using independent power domains, the processor, L2 cache, and debug systems can be controlled separately. The figure on the slide shows the Cortex A72 power domains. These capabilities allow the same processor to be configured for high performance mission or low performance mission, thus giving its versatility. To thoroughly evaluate the ARM processor, the authors conducted two sets of benchmarking. The first set is synthetic benchmarks, where the author used Drystone for integer operations, Whetstone for floating point operations, and CoreMark for general embedded workloads. This gives a baseline comparison against existing space-qualified processors like the GR712RC, UT699, and the MPC8548E. Then comes the second set of benchmarks, which involves real-world tests. The authors used JPEG-LG LS compression decompression, which is very relevant to imaging systems important in space missions. Also, the authors conducted mobile net SSD object detection, which represents modern edge AI workloads. The goal was not just to test raw speed, it was to see whether ARM can match or exceed current processors at comparable power levels. The result was striking. Drystone and Wheatstone, these benchmarks are single-threaded, so performance scales with frequency, but not with core count. Even at the lowest ARM frequency, the ARM processor outperformed all legacy processors by a significant margin. And since CoreMark can use multiple threads, results improved greatly with more cores. At maximum frequency and 4 cores, the ARM achieved 38,000 plus core marks, or almost 24 core marks per megahertz, a massive improvement over older processors. But the takeaway is this, even at restricted frequencies, with one core, the ARM processor exceeds the performance of processors currently used in spaceflight. The authors also measured power consumption at various frequencies and core counts. The ARM processor could not reach ultra-low power levels comparable to the GR712RC or UT699. because those are designed for extremely low frequency operations. However, when compared with the MPC, a widely used high performance space CPU, ARM consumed significantly less power while providing dramatically more computation. To make the comparison between MPC and ARM Cortex processors fair, the authors ran both the processors at 800 MHz. The MPC achieved a core mark score of about 3500 plus, whereas the ARM Cortex achieved 18,643, over 5 times faster. And also, it did this with much lower power consumption. This shows that ARM isn't just faster, it's also more efficient under identical operating conditions. For many future missions, this can translate to increased capability without increasing power budget. The authors tested JPEG-LS, which is widely used for space imaging because it's lossless and efficient. Using an 8 megapixel grayscale image, the MPC took about 8.6 seconds to encode the image, where the ARM Cortex took only 414 milliseconds, so it was more than 20 times faster. Both processors produce identical decoded image, confirming the ARM achieves the speed up without sacrificing accuracy. For imaging-heavy missions such as Earth observation, mapping, or star tracking, this improvement is substantial. As machine learning becomes more common in spacecraft for tasks like star tracking, anomaly detection, or onboard data reduction, the authors also evaluated ARM using mobile net SSD. These configurations were tested ARM neural network with 32-bit floors and TensorFlow Lite with 32-bit floors and 8-bit integers. The ARM neural network 14.32 backend performed best with 8.8 frames per second throughput, 113 millisecond latency, and a highest accuracy of 23% MAP. Interestingly, the integer 8 model was lower in this environment than the FP32, likely due to implementation overhead. To summarize, the ARM Cortex A72 provides significant performance gains over existing space processors. It can also meet a broad range of computing and power requirements. And of course, it enables platform reusability, reducing cost and engineering efforts for future missions. Lastly, though it is not ideal for ultra low power missions, but is excellent for moderate and high performance platforms. The future research will focus on evaluating advanced dynamic power features, also long duration benchmarking to confirm stability, and crucially, conducting radiation testing to validate its suitability for high radiation environments. Overall, the ARM-based processors show great promise for next-generation spaceflight embedded system. Thank you very much.